1s2, 2s2, 2p6, 3s2. Oops. Get a little sloppy here. Okay, so how do we fill for Fe3 plus? So for the rule for transition metal ions is that we fill the D set first before filling the S of the next N level. So how many electrons am I going to take off of iron neutral to get to iron 3 plus? I'm going to take off 3. So of these 8 now, I have to take off 3. Of these 8. Where do I take the 3 off? I take them off the 4s, and I take one of these out of the 3D, right? And so what I end up getting is just that, okay, a half-filled 3D sublevel. And that's the rule for transition metal ions. And if you think about it, why does iron tend to form +2, +3 ions? Well, if you take off 3 electrons, and you start by taking out the 4s first and taking out the 1, 3, there's something called the half shell rule that the atoms favor. So keeping a perfectly half-filled sublevel is more stable relative to disrupting that. If you can hold it, they generally will. Okay, so it kind of makes sense. And then what would be an Fe2 plus? How would that change? Yeah, if this was Fe2 plus, you would add 1 to the 3D, not 1 to the 4s, right? It would still be in the 3D. Okay, so the rule is that for cations, you fill the Ds first, then you fill the 4s. Okay, that's the rule. Yes.
So you always want to complete the sequence of the whatever number it is, and
Right.
then move on to the
Right. For the transition elements.
For the transition.
Yeah, for the transition elements. Okay, so this experimental evidence kind of, or this idea of leaving spin. So if you look at iron 3 plus, it has a lot of electron spins that are parallel, right? Although there's quite a few here in iron neutral. So atoms that have unpaired electrons are attracted to a magnetic field, while those that have completely closed subshells are slightly repelled. Okay, so if you have nothing but filled subshells, for example, the noble gases, they have completely filled subshells, there's no unpaired electrons. Those are slightly repelled by magnetic fields. But if there's unpaired electrons, they'll be attracted to magnetic fields. So substances that are attracted to magnets are said to be paramagnetic. So if you have an atom with an electron configuration with unpaired electrons, you would call it paramagnetic. And if all the electrons are paired, you call it diamagnetic. This is terminology. So is iron paramagnetic or diamagnetic? It's paramagnetic. It's got unpaired electrons. What about Fe3 plus? Is that para or diamagnetic? Yeah, that too is still paramagnetic. It still has unpaired electrons. What about antimony? Paramagnetic or diamagnetic? It's also paramagnetic, right? So many of the elements, most of the elements, or majority of them, have unpaired electrons. Why aren't more of the elements magnetic than in general? All right, and that has to do with ferromagnetism. Okay, that's not in your textbook, but most of the elements actually are not magnetic. Okay, and the reason why is because if you combine an iron atom with another iron atom, the unpaired electrons from the other iron atom will spin pair with the unpaired electrons in the neighboring atom. Okay, and so there are very few elements that actually exhibit true magnetism. Okay, because most of them will have electrons that spin pair. Okay. Here's the question. Use orbital energy level diagrams to show whether zinc 2 plus or titanium is paramagnetic. So we have zinc 2 plus, and we have titanium. Okay. 1s, 2s, 2p, 3s, 3p, 4s. 3D, right? Alright, and then we do titanium, same thing. Okay, so let's look at zinc 2 plus. How many electrons do I have in zinc 2 plus? So zinc is atomic number 30. It would have 30 electrons for a neutral atom. How many electrons are in the zinc 2 plus? 28, right? So I'm going to pile in 28 electrons into this according to the Aufbau principle in Hund's rule. So here's 2, 4, 10, 12, 18, okay. How do we fill in here? Transition metal cation, we fill the D first, right? So we have 2, 4, 6, plus another 12, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. We don't have any more electrons to fill it for us. For titanium, how many electrons are in titanium? 22, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18. 4 more. There's 22 for titanium. So which one is paramagnetic, which one's diamagnetic? Yeah, zinc 2 plus would be diamagnetic. Titanium would be paramagnetic. Question?
I thought that we only filled up the D syllable first with ions, like medicinal ions.
Oh, you're right. I'm sorry. Okay, so yeah, you're right. The 4s2 gets here. Good catch. Yes. So it's still paramagnetic, but yeah. All right. So now you can kind of see why zinc always forms 2 plus cations, right? Because the S's come off. Right, there's nothing in the S you maintain a full 3D sublevel, and Zinc likes to do that. Any other questions about this? All right. There's another term you should be familiar with called isoelectronic. So species that are isoelectronic to each other have the same number of electrons, and hence they have the same ground state configuration. So here's an example. If I look at sodium plus, the condensed electron configuration is just neon. Right, so you take take an electron off of sodium, it becomes like neon. Take 3 electrons off of aluminum, again it's like neon. Add an electron to fluorine, you get fluoride. Again, that's the same as neon for the electron configuration. Add 2 electrons to oxygen, you get oxide. That again is like neon. Nitride comes from adding 3 electrons to nitrogen, you get neon. So you can say that sodium plus, aluminum, fluoride, oxide, and nitride are all isoelectronic with each other. Okay, they're all also isoelectronic with neon. Okay, so it's just a term that you should be familiar with. Here's a question for you: what neutral atom is isoelectronic with hydride ion? Helium, right? So hydride has 2 valence electrons in it. Its configuration is 1s2. That's the same as neutral helium. All right. So that's it for today. I'm gonna stop there. Today it shouldn't have been too bad though, right? It was a lot more tame. Or somewhat more tame. The whole screening thing takes a little bit of time. Right? Just think, everybody has a wave function. Some people infiltrate more.